Hey guys, I just wanted to make you a video over periodic trends because I feel like went over it pretty quickly, and I know some of you were absent, so I just wanted to talk about it. Periodic trends are governed by something called periodic law, which is the idea that when elements are arranged in order of increasing atomic number, that there is a periodic repetition in their properties. That's a long way of saying when the periodic table is arranged how it is, there are some trends in the way the elements behave. So, on this periodic table, I have drawn some atoms for you, okay? And if you notice, on the first energy level, they have one circle, the second 2, 3, 4, 5. But then I want you to notice, I've also drawn just one period, which is across the periodic table. I've drawn one period for you as well. I've skipped the transition metals because we know things get complicated there, and you can kind of see what's happening on the periodic table without looking at transition metals, okay? So as you go down the periodic table, atoms get bigger, and as you go across, they get smaller. And that's the first trend that we talk about, okay, is atomic size or radius, okay? As you go down the periodic table, atomic size increases. As you go across, size decreases. So Fr, which is right here on the periodic table, is the biggest element, and then helium here would be the smallest element. Why? The downward trend, okay? When you go down the periodic table, we add more and more energy levels. And if you look at the picture that I drew for you, more and more circles are added to the atom. Think of that as like layers of a sweater, okay? So, additional layers of clothing. The more sweaters you put on, the more bulky you become, okay? So more energy levels are added. If you look at hydrogen versus rubidium, hydrogen has one circle, rubidium has many, and those are in the same group. So as you go down, elements go from small to big, okay? Now across, this trend is one that students struggle to understand because as you go across, they get smaller, but they have more particles. So how does this happen exactly? Well, as you go across, there are more protons in the nucleus. So I have written here, across the periodic table, the number of energy levels remains the same, but the atomic number, which is equal to the number of protons, increases. This increases Coulombic attraction. This word I have written here, Coulombic attraction, is really important. It is the attraction that happens within an atom due to opposite charges within the atom, okay? So as we go across, there's more opposite charge, so that's more attraction. More attraction equals a smaller atom, okay? The more attraction you have, the more tightly the nucleus pulls in the electrons and the smaller it is. The example I have for you here is sodium and chlorine are on the same row on the periodic table, okay? And let me see if I can find a periodic table to show you. Sodium is here, chlorine is here. They're on the same period on the periodic table, so they have the same number of energy levels. But chlorine has 17 protons in its nucleus. That's 17 positives pulling on its electrons, whereas sodium only has 11. Since chlorine has a greater opposite charge, it has more attraction, Coulombic attraction, within the atom than sodium does, so it's smaller. As we go across the periodic table, Coulombic attraction, or the increase in Coulombic attraction, decreases the size of the atom, okay? And this is another example too. Potassium versus bromine. Potassium and bromine. Same period, but bromine is almost all the way to the right, and potassium is on the left. Potassium only has 19 positives in its nucleus to attract its valence, whereas bromine has 35. Greater in opposite charge, greater pull on electrons. The next trend we're going to talk about is ionization energy. And ionization energy, as you go down the periodic table, decreases. As you go across, ionization energy increases. Let's talk about why. When you go down, we already know that there are additional energy levels in the atom, okay? And that creates layers of electrons that the nucleus has to fight through to attract its valence. Okay, now why does this matter? Let's go back to the definition of ionization energy. Ionization energy is the energy it takes to steal an electron from a neutral atom. Okay, so the further down you go on the periodic table, the more of these inner layers of electrons shield the valence from attraction. So the easier it becomes to just steal an electron because there's so many inner layers of electrons, okay? And that is this shielding effect. This is really important that we know. The more shields you have, the less energy it takes to steal that electron, okay? So if we look at barium and magnesium, okay? Barium has 1, 2, 3, 4, 5, 6 layers of electrons. So that's 5 inner layers of electrons. So it's not attracting its valence nearly as well as magnesium, which only has 1, 2, 3 layers of electrons, 2 inner layers of electrons. So barium would have a much lower ionization energy than magnesium, easier to steal from barium, okay? All right, the horizontal trend as you go across. We already talked about the increase in Coulombic attraction, okay? If I am very attracted to my valence electrons, it's going to take a lot of energy to rip them away, okay? So if we look at, let's say, titanium and bromine, bromine has 35 protons when compared with titanium, which has 22. Bromine has a higher Coulombic attraction, therefore it's going to take more energy to steal from bromine than it will titanium, okay? That's ionization energy. All right, now, electronegativity. The definition of electronegativity is the amount that an atom attracts electrons within a bond, okay? So I want you to notice ionization energy and electronegativity, they have the same trend. They decrease downwards and they increase across. Why? Because they're both about how much an atom wants electrons. Ionization energy is how much does an atom want its own electrons. Electronegativity is how much an atom wants somebody else's electrons, okay, within a bond. So the trend is the same. And honestly, the reasoning is pretty much the same as well, okay? Downward trend. We have increased shielding. The nucleus can't attract someone else's electrons if there are tons and tons of layers between the nucleus and someone else's electrons, okay? And the horizontal trend, the same thing. You have increased Coulombic attraction within the atom, more protons in the nucleus, more of a positive charge to attract electrons within a bond. Same as ionization energy, okay? So those two are going to be the same. Now, if you have any questions on this, let me know. I think that should have covered all that we talked about the periodic trends. Now, let's talk about Lewis-Dot structures. Lewis-Dot structures are all about reaching an octet, okay? Everybody wants 8 except hydrogen. Hydrogen is okay with 2 because then it's like the noble gas helium, okay? So the first one on your Lewis-Dot worksheet is HCl. So you start off by drawing the Lewis-Dot of each of those elements, okay? How do I know how many valence electrons they have? Based on their group number. Group 1 has 1, 2, skip the middle, 3, 4, 5, 6, 7, 8, okay? With the exception of helium, helium, you know, has 2, except it's over there because it's a noble gas, okay? So, when these form a bond, these 2 electrons become shared between hydrogen and chlorine, okay? And hydrogen, it thinks it has 2, so it's happy. It thinks it's like helium. Chlorine thinks it has 2, 4, 6, 8, so it's happy. It thinks it's like a noble gas, okay? And we show that like so, okay? You can have single bonds, which just represent 2 pairs, or 1 single pair of electrons or 2 electrons. You can have double bonds, which represent 2 pairs, and triple bonds, which represent 3. And remember, everybody wants 8 except hydrogen. Let's do another one. I think number 3 on your worksheet was NH3. Now, NH3, we have more than 2 atoms, right? So the central atom becomes the one you only have 1 of. So nitrogen, because of where it's at on the periodic table, has 5 valence electrons. Notice I put 1 dot on each side before I pair them up, okay? And then I have 3 hydrogens. How do I know I have 3? I have subscript 3 here, okay? And then I can see these guys are going to form bonds. How do I know which electrons are going to form bonds? The ones that are unpaired. So see how in chlorine it only had 1 unpaired electron, and that was its opportunity for bonding. Hydrogen, same thing. On nitrogen, it had 3 unpaired electrons. Those are the ones that it's going to form a bond with, okay? So this becomes, and then notice I'm also going to take those non-bonding electrons and I'm going to copy them here, okay? So that's how you deal with single bonds. Now let's look at number 8, which is CO2, okay? Carbon, according to where it is on the periodic table, 4, oxygen 6, and I have 2 oxygens, okay? So I'm going to put the C, it's in the middle because there's only 1 of them, and then I'm going to put the O's next to it. Carbon has 4, oxygen has 6, okay? So carbon always forms 4 bonds because it has 4 single electrons, okay? So we can see that there's 1 opportunity for bonding here, but we're not done, okay? We're gonna have double bond with both of these. Why? Because oxygen needs 8. It has 2, 4, and then it also thinks it has these 2 sets, which are make it 6, 8. Carbon thinks it has 8, 2, 4, 6, 8. Oxygen thinks it has 2, 4, 6, 8, okay? So everybody thinks they have 8 in this situation. And we have no unpaired electrons, which are unstable, okay? And that's pretty much it. That's how you do Lewis dot. That's a double bond. These guys are single bonds. Let me know if you have any questions.